just time to listen to our guest, and the floor is to you, Professor Soutis.
Thank you very much. It is a great pleasure to be here today, and good afternoon to Bordeaux as well. I hope that they can see us and we can communicate with them. Before I talk about graphene, I would say a few things about the talk outline. I'll say a few things about the University of Manchester, who we are, and then talk about graphene at Manchester, and possible applications of graphene in the aerospace sector, but also in other sectors outside the aerospace industry. Of course, if I talk too fast, you can tell me to slow down. You can interrupt during the presentation, or we can take questions at the end of the seminar. We are the largest single-site university in the UK, with a history going back to 1824. And some key facts, we have about 40,000 students, 10,000 staff, and 25 Nobel Prizes over the history of the university. It is the birthplace of the Industrial Revolution, and the atom, of course, was split at the University of Manchester and not Cambridge, as they claim. Is the first programmable computer was developed at the University of Manchester. And currently, eight of current world leaders, 4 prime ministers and 4 presidents, are graduates of the University of Manchester. Only Oxford has 9. Graphene is another thing that has been made in Manchester. It is the largest single graphene research group with over 200 researchers, and a total income over the last 4 years of 170 million pounds. You can convert that into euros. And it brings together, it's a very multidisciplinary institute that brings together mathematicians, physicists, material scientists, and of course, engineers. The National Graphene Institute opened in March 2015, and as I said earlier, it's an opportunity to bring communities, different communities, under one umbrella, to tackle problems that they are multidisciplinary by their nature. And of course, aerospace is one of those multidisciplinary areas where you need the chemist to look at the polymer. You need the physicist to understand the microstructures, the material scientist. But at the end of the day, the engineer who is going to build and identify applications where those new material systems can be really exploited. So the National Graphene Institute is led by academics, and it provides an opportunity to demonstrate new concepts, new applications, demonstrate the potential of graphene by producing new products, and assist in the development of low-cost and scalable manufacturing methods for high-quality graphene. Because today, you might go on Google and say, I would like to order 1 kilogram of graphene. The big question remains how pure that graphene is. What do you know about its purity? And of course, it all depends very much on how it has been manufactured. Of course, the advantage that we have in England is that the weather is not as hot as in Toulouse, so I need to take off my jacket. Excuse me, Bordeaux, for removing my jacket. But, and the other important aspect and big challenge with graphene is the process stabilization, and also develop a method that is reproducible. You can reproduce it without affecting the quality of the material. And the other important aspect is how to develop standards to qualify, to quantify those material properties that we are looking for. And the focus of this National Graphene Institute is from 1 to 4 TRLs. So it's more fundamental research. Now, in addition to the NGI, we have the Graphene Engineering and Innovation Center, which is another 100 million euros activity, which is led by industry in collaboration with academics. And as we can see, in this case, the focus is at higher TRLs. So we're talking about 4 to 6, which is probably similar to the TRLs that you're examining under the IRT. Now, today the talk is to identify applications of graphene in composites, and more specifically, in polymer-based composites, where the matrix is a polymer, and in my case, mainly thermosets rather than thermoplastics. And we can see from this picture up there, these composite material systems, they're multi-layered, and the fiber orientation depends very much on how your component, how your structure is supported, and how your structure is loaded, and then the stress analyst optimizes fiber orientations. And we can see some of the earlier applications of carbon fiber reinforced plastics go back to 1983 with the tennis racket, and a bit later on in 1985 with the McLaren Formula One car. So as we can see, although carbon fiber epoxy systems have been developed in the kind of late 60s, we've seen the first applications appearing in the early 80s. Airbus introduced composites in their Airbus A300 in the late 70s, early 80s in the form of control surfaces, and it was mainly glass reinforced plastic. But composites became more popular in the early 80s onwards. So you can imagine now, if we bring in graphene into composites, it's going to take a bit longer to identify those applications. So if we look at the application of composite materials in the Airbus aircraft, we have seen that the usage of the material grew exponentially, where we've reached today in the Airbus A350, where more than 50% of the structure is made out of carbon fiber reinforced plastics. And the question is, of course, have we reached saturation? Can we build the whole aircraft out of carbon fiber reinforced plastic? And what materials will be used in the next generation of the Airbus or the Boeing aircraft? And trying to identify ways to see if graphene, for instance, can be used in combination with traditional carbon fiber epoxy system to give us some kind of superior properties. Because as we know, when we build with composites, yes, we benefit from the increased stiffness, the strength, and the reduced weight, which of course you need in order to have a light structure to fly. But they do get damaged. You drop things, and they behave in a more kind of brittle manner. And in this case, for instance, we can see that we don't need a non-destructive evaluation technique. We don't need an SHM system, because with naked eye, we can see the damage. And the challenge we have here is how to fix the damage, how to repair it. And that remains a big challenge for the operator. But from the graphene point of view, can we use graphene to make our existing composites more resistant to impact damage. So can we use graphene to make the current carbon epoxy systems more damage resistant? That will be good, because if we can do that, then we don't have to worry about repairs. Because performing a bonded repair in a primary structure, it remains a big challenge, because actually the EASA and the FAA, they don't certify bonded repairs. So if you have damage in the primary structure, you have to drill holes, and your patch has to be riveted. But what is the problem with rivets? What is the problem we have with rivets? We have to drill the composite. By drilling, we cut fibers, and then we go back to stress concentration factors that we have to deal in metallic structures. And when we say composites do not fatigue, we know very well now, once we have holes and rivets, fatigue can become an issue, especially as we moved to an era where now our composite structures are becoming primary structures and are heavily loaded in comparison to composites in the early 80s or late 70s, early 80s, when they were used mainly as secondary structures. And of course, the other big problem we have currently with carbon epoxy systems is that when they're loaded in compression, the compressive strength is only 60%, 70% of the equivalent tensile strength. And the reason behind it is because there is a huge mismatch in thermal properties between the carbon fiber and the polymer. So if you look at the coefficient of thermal expansion of your polymer, of your resin, is about 70 to 80 microstrains per degree Celsius. While the coefficient of thermal expansion of your carbon fiber is -5 microstrains per degree Celsius. So during the cooking process, you develop thermal strains which are high enough to distort your fibers. So your carbon fiber of a diameter in the region of 6 micrometers becomes wavy. And when the structure is loaded in tension, the wavy fibers become straight. But when your structure is loaded in compression, the wavy fibers fail in the mode of fiber microbuckling, which is a fiber instability failure mode that takes place at the fiber level. And although the structural engineer has designed his structure to avoid Euler buckling, you can still fail in the form of fiber microbuckling, which then reduces the strength by up to 40%. And then the question is, can we develop now resin systems that they're thermally more compatible with your carbon fibers? Can we use graphene to nanomodify the polymer to make it more compatible with the carbon fiber, to reduce the fiber waviness and improve the compressive strength, which remains the critical design parameter for modern aircraft structures? So we've seen then a potential there, a potential for graphene to be used in carbon epoxy systems where we can improve the strength, the stiffness, the toughness. We can make the composite more damage resistant. And when eventually damage does happen, we can probably tolerate that damage. So we can design then more damage tolerant structures. And then when we move away from just mechanical properties, can we use graphene to modify and introduce electrical functionality? Can we increase the electrical conductivity of the carbon epoxy system so when our aircraft is exposed to a lightning strike, it doesn't get damaged? It behaves like a metallic airframe. Can we do that? Or can we use graphene to improve the thermal conductivity of the composite? So as you can see, there are options there where graphene can introduce some kind of multifunctionality in our carbon epoxy systems, which we have seen that they're used extensively by the aircraft industry, the sports industry, the automotive industry. But of course, the aircraft industry remains the sector that actually invests and drives technology. They set all the challenges that we are facing today. Because after all, yes, the Formula One uses carbon fiber reinforced plastic, but if you go to Formula One to ask for research funding, they're not interested on research. They would like to use existing research. But then, of course, the question becomes, what is graphene? What do we know about graphene? And how new is this super material? So graphene is defined as a two-dimensional material. It's an allotrope of carbon. It is one atom thick, which is 0.33 nanometers in thickness. And we say there it is accepted with up to 10 layers of graphene, still is considered graphene. But then, of course, we are familiar with 0D, the baggy balls. Carbon nanotubes, they're one-dimensional graphene. And the three-dimensional product, of course, is graphite, from which we can extract and produce graphene. And of course, people talk about the limitless potential. And they talk about the high strength, the super light weight. It's 97.7% transparent. In addition, of course, to super stiff, super strong, super light, there is another huge list of graphene superlatives, I call them, that give you the impression that they can solve all our problems we are facing today. Thermal conductivity, electrical conductivity, and so on and so forth. This is a very, very long list of properties that they make this material to be defined as super material. And if we look at some properties like, say, stiffness, it's in the region of 1 terapascal. And if we look at strength, it's 130 gigapascals. While if you compare the stiffness of currently used carbon fiber systems, the stiffness of carbon fiber is in the region of 250, 300 gigapascals, while here we're talking about 1,000 plus gigapascals. And if we look at the strength, it's in the region of 2.53 gigapascals, while here we're talking about the strength of 130 gigapascals. How can we measure those properties? It's not easy. First of all, you need to have the graphene flake. And second of all, you need to develop the test methods and the measuring equipment, the strain gauges, yes, to measure stress and strain in order to calculate stiffness and in order to capture the entire stress-strain response. And we can see here an example where you have this cantilever beam with an AFM tip nanosensor to measure the strain developed on that graphene flake. And from the stress strain curve, we can see that we have the very high strength of 130 gigapascals and the Young's modulus of 1,050 gigapascals. And then when we look at the comparison of graphene with other traditional materials, we can see that graphene is at the top left corner with very high stiffness and very low density. So you can see where the traditional carbon fiber is much lower. And of course, if we look at steel, it's got a specific stiffness of 25 units compared to 500 units for the graphene. So it is a super material. But of course, the problem that we have to face, it appears here with the comment in red. Like all carbons, the manufacturing route determines the properties and, of course, ultimately, the cost. How much are you prepared to invest in order to achieve those super properties? And what are the applications where you need those super properties? So you need also to identify where to use that material. And as we said at the beginning of the talk, there is graphene and its derivatives. So we have the graphene here produced with the CVD, Chemical Vapour Deposition. Then we have the graphite, the reduced graphene oxide, the graphene oxide, and the graphite oxide. So when you go out to buy some graphene, what do you buy? Do you buy pure graphene, or they give you some graphene oxide? Or they might give you graphite oxide, which is going to have completely different behavior and different properties for the pure graphene. Of course, the next challenge we have is how do we make graphene? Yeah? And one way to make graphene is we can start with a top-down method where we have a block of graphite and we try to break away layers of graphene. Or we can go from bottom up, where we can build graphene atom by atom. And there are these kind of two different techniques that they can give you graphene. But if we look at the first two-dimensional graphene material, we have to go back to 1 to 5 layers of material identified by my colleagues at the University of Manchester back in 2004. And then, if we look at this graphite trace on the oxidized silicon wafer, they went to one small spot, tiny spot. There's the spot, isn't it? I mean, that's a small spot there, which is probably kind of, yeah, this kind of spot there, pencil spot there. And then if you magnify that, there you are, that's your first flake. That's the first 2D material, which was demonstrated by the colleagues at the University of Manchester. And of course, you can produce your own graphene using the Scotch tape exfoliation technique. Yeah. So next time that you go to Stockholm, at the museum, you're going to see a lamp of graphite. Yes, the Scotch tape, and also they have donated a graphene transistor. Yeah? They're on display at the Science Museum in Stockholm. I have some pencils here, of course, from Manchester that you can use your own Scotch tape to produce your own graphene. But of course, my pencil is more kind of multifunctional, yeah, because also it can fly. You see, so I can give one to your CEO there. You can catch that. There you are. Enjoy flying. So, if we go now to the graphene production, we've seen that one method is the electrochemical exfoliation, not as simple as the Scotch tape, of course, but it's more complicated than that. And the University of Manchester has the IP for this electrochemical exfoliation, where we can produce pure graphene with those super properties that we've seen earlier. The problem we have is that we can produce only a few grams, because after all, we're a university, we're not an industry. Yeah? And this is where then the National Graphene Institute and the Engineering Graphene Center, they can work closely with industry and take those concepts, and probably next time they can give us, instead of few grams, they can give us few kilograms. Yeah? And at the moment then, we say we produce few graphene flakes. They are few layers thick. Small sizes, you can see there the distribution of size, anything between 140 to 300 nanometers, and the thickness around 2 nanometers, or less, or slightly bit more, few layers. And then what can you do with those grams of graphene? As we said earlier, we can modify plastics. In this case, we can modify a thermoplastic with the ultimate aim to improve strength, stiffness, toughness. But then again, I wouldn't waste my graphene to improve the mechanical properties of PMMA. Why am I going to do that? Even if I double or triple or quadruple my stiffness, still I can't really build an aircraft with that kind of material. But it's to demonstrate that how you can mix it, because the mixity and distribution of graphene has a huge impact on the properties that you will achieve in your final product. And also you want to demonstrate that as you increase the amount of graphene, you don't alter viscosity. And we can see in the top left graph, if we have the 5 micrometers graphene flakes, as we increase the amount of graphene from 1% to 10% by weight, we don't alter the viscosity. If our graphene is of a larger size, 20 microns, graphene flake, then we can see as you increase the amount of graphene in your polymer, then you change the viscosity, which it means that it's going to have an effect on your manufacturing process. And then if your thermoplastic is reinforced with continuous fibers, then maybe the effect or the benefit that you will get from graphene, it's not really felt as much. So these are critical issues on how we can mix and disperse uniformly the graphene in our matrix. And if we look at the Young's modulus, we can see that from 2.4 gigapascals, we have increased it. In percentage terms, it's very high increase, but in actual terms, again, what am I going to do with 3 gigapascals stiffness? maybe some people in the electronics industry or some other industry, some other sectors, they're going to say, oh, this is a very significant increase, and I will benefit from that. But from the aerospace application, I cannot build anything with that. Now, if we look at other properties outside mechanical response and mechanical behavior, if we look at thermal conductivity, we're going to see that we can increase the thermal conductivity dramatically. And that is a beneficial thing, especially when in the aircraft industry, we would like to do something about heat management and how we can dissipate heat quickly in a non-metallic structure. So then there we can see straight away a huge benefit by modifying the thermal properties of our component. And you need appropriate equipment to make those measurements for the thermal conductivity. The other significant property that we mentioned at the beginning of the talk is the electrical conductivity. And if we look at thermostats or thermoplastics, they are not electrically conductive. They resist electrical flow. But if we introduce 2% by volume graphene, then we can see that the electrical conductivity increases by 12 orders. So that is a significant improvement. Of course, someone might say the electrical conductivity of copper is 10 to the power of 9 Siemens per meter, which then again, I'm far, far away from that conductivity of copper. Now, the conductivity of the pure graphene flake on its own is similar to copper, but when you mix it with the polymer, then obviously it's much lower, but still 12 orders higher than the monolithic polymer. Another way of producing graphene is by chemical vapor deposition. And we can see there, atom by atom, we create the layers of graphene. So you grow graphene on your copper substrate at elevated temperatures of about 1,000 degrees Celsius. Again, there is an IP behind this, because it's not as simplified as it appears on the screen. And if you go at the small scale level, then with those graphene flakes, you can develop strain gauges. So you have straight away an application of graphene strain gauges for your applications in microelectronics and many other industries where when you measure strains, they are in few microstrains rather than the thousands of microstrains that we experience in structural applications in the aerospace. And of course, the advantage with graphene is the opportunity to build multifunctional composites, where certain layers in our multi-layered composite construction can be responsible for providing the strength, the stiffness, the optimized toughness, the heat storage or dissipation, or they can act as sensors to detect damage in the composite structure when the composite structure goes into service. So they can sense impact events. So when the aircraft mechanic walks along the aircraft composite wing and drops the spanner, the graphene can act as a sensor to report the impact event that took place. So here we have a multi-layered construction where it has been optimized for different functions. So we have a multi-layered, multifunctional composite structure. And then people ask me about applications. Already we mentioned applications where we can modify mechanical properties in our polymer. We can modify thermal properties, electrical properties, but also we can build things. We can look at electronics, special coatings. We can look at photonics, graphene sensors. And if we go back to 1983, focus on the racket, not the legs, we can see that straight away, an application of graphene is, again, for commercial purposes, a tennis racket. You remember the 1983, where people, they used the carbon fiber to produce the first composite racket? Already in the market head, they advertise their first composite tennis racket reinforced with graphene. And of course, people is prepared to pay a premium price because on the frame of the racket says graphene reinforced. It's the same mentality as in 1983 when people paid for the carbon fiber racket. Another application is that if you look at your iPhone, people usually drop them and the screen shatters. If you can replace the screen with a cheap plastic which is coated with graphene, then it doesn't matter how many times you drop your phone, it's going to be unbreakable. Question mark. You can use graphene maybe to develop the next generation of graphene charger. So you can charge your iPhone in a few seconds. You can upload data in a few seconds because you remember that graphene flake provides no resistance to flow of electrons. I like this one, graphene filters, where the filter allows the water to go through, but it arrests the salt, so it purifies seawater. Graphene supercapacitors. You can get rid of batteries, because this is my proper UAV in my office that I fly. Of course, the propeller in addition to that. But my battery runs out very quickly. I can fly that for about 10, 15 minutes. Recently, I managed to fly that for about an hour. But I had a tether connected to the battery of my car, which is then, it's not really autonomous, isn't it? So if you really want to go to a long duration flight, maybe we need something more special there than the batteries. It can be used for applications in bioengineering. This is a project funded by Bill Gates and Melinda Gates Foundation, where the objective of that project is to develop graphene condoms, that they don't burst as easily as the commercially available ones. It's a big issue in Africa. Again, the difficulty there is on the dispersion, but we're getting there. 3D printing of graphene composites. If you look at currently 3D printing, it's all monolithic materials with no reinforcement. Maybe this is an area where actually graphene can be applied more easily. We spoke about lightning strike protection, and we spoke about coatings. But then again, this is kind of more difficult application, more difficult to really accomplish and achieve. If we look currently at the composite airframes, like the Airbus A350 and the Boeing 787, in order to protect the aircraft from a lightning strike, it is covered by a chicken wire. It's a mesh, a wire mesh, that puts additional load on the aircraft. And if you go back to the earlier impact damage where the composite airframe has been damaged and needs to be repaired, now, in addition to repairing the airframe, you have to make sure that you have repaired also the protection of the aircraft. So the question remains, could a conductive graphene modified epoxy matrix provide protection? Maybe not today, but I don't know. Maybe something that can happen in the near future. So some conclusions. We have seen that carbon fiber epoxy systems, they're used extensively in the aircraft industry. 53% of the Airbus A350 is CFRP. We've seen that graphene could be introduced into composites to modify not only the mechanical properties and the resistance to damage and the damage tolerance, but also the thermal aspect, the electrical aspect. But then again, the aircraft industry is a very conservative industry, and it can take a long time before new materials become widely used. And always, for very good reasons, the certification of new materials can take many years. But then again, maybe this is again an area where institutions like the IRT and our institutions in Manchester can convince the certification authorities that we have developed the appropriate mathematical models that can reduce the amount of mechanical testing to give them confidence and trust our designs without actually breaking so many coupons, sub-elements, elements, components, substructures, and the whole structure. So if you look at the whole test pyramid that Dolphin can explain to you, it's a very expensive and time-consuming process. And that's where we need the mathematical skills and computational skills to give us confidence so we don't have to do all that mechanical, high-growth thermomechanical characterization of those new materials that we try to introduce in the aircraft sector or any other sectors of our economy. It can be the marine, the automotive, space, sports industry, bioengineering, you name it. So, another question, graphene composites, is that the future? Maybe. Already we've seen practical applications, engineering applications, commercial applications. And you've seen again the Formula One. They're very keen to introduce parts in a Formula One car that contain an amount of graphene. But we have all these barriers and challenges to deal with. First of all, the first one is to burst that hype bubble. Yes? Yes, graphene is super material, but yeah, we have to be careful with what we can achieve. What we can achieve in the short term, in the medium term, and in the long term. We have to think about the manufacturing of graphene. Can we reproduce it? Can we produce enough quantity to use in our structural applications? And we have to clearly demonstrate of the advantages that we'll gain by introducing graphene into our structural applications. We have to deal, of course, with confusing nomenclature. There are so many names out there. And we spoke about purity earlier. There are no standards. So again, the community and the industry, they have to set up standards. And of course, at the moment, we have no that killer application where really we can demonstrate that all this investment on graphene has paid off or will pay back very soon. So we're still looking for that killer application. And then, of course, we spoke about applications in biomedical sciences. But before we do that, we have to think also about health and safety uncertainties. Because, yes, you might introduce new sensors, new devices that can be implanted. But before we implant them into our body, we have to make sure that there is no interaction or chemical interaction or health aspect. So, to finalize then, the National Composites Institute in Graphene, the Graphene Institute in Manchester, it provides an opportunity for collaboration, an opportunity of collaboration with industry, but also universities and other institutions. It provides access to personnel and equipment that can be used to investigate aspects of graphene, and also can assist how the concepts we develop at our centers can be smoothly transferred to industry, where their job is entirely to produce new products that they are more efficient, more advanced, more reliable, and our industry can be more competitive and survive in the long term. Some of the industry partners that currently are working with us at the University of Manchester, these are some of the Graphene Colleagues that I'm currently working at the University of Manchester, and you can find them more details on their websites. I can advertise some of my new books, Polymer Composites in Aerospace Industry. Am I allowed to do that? It's too late now to stop me. This is the latest one on structural integrity. Something that Dolphin can advertise to Airbus colleagues. Mingling with the royals. This is Prince Philip. I was elected to the Royal Academy of Engineering in 2014, and I was invited to meet Prince Philip. So anyway, thank you very much for your attention. Thank you, and I'll be happy to ask questions. Thank you.